Hello everyone, welcome to robotics module. Today we are going to discuss manipulator singularities. This is the outline. First we will have a recap on what we studied last time. Next we will have a brief introduction to singularities. And then we will look at how we can determine the singularities of a given manipulator. We will do some examples and finally we will look at inverse velocity. So last time we looked at the two parts of the manipulator Jacobian, the linear velocity Jacobian JV and the angular velocity Jacobian J omega. And we derived expressions for both these Jacobians, and putting J omega and JV together, the ith column of the complete Jacobian matrix was given by this expression if the joint is revolute, and by this expression if the joint is prismatic. Today we will look at the singularity configurations that can occur in the manipulator. The Jacobian JQ is a 6 by n matrix that defines the mapping between the Cartesian velocity vector and the joint velocity vector. Now all the possible end effector velocities are going to be linear combinations of the columns of the Jacobian matrix. So we have J equals J1, which is the first column, J2 is the second column, and we have Jn to be the nth column. So the end effector velocities will be linear combinations of these column vectors. Last time we derived the Jacobian matrix for the two-link planar manipulator. So it was a 6 by 2 matrix, 6 by 2, and we could observe that the manipulator is unable to achieve any linear velocity in z direction, as well as it cannot achieve any angular velocities in x and y directions. Okay. Now if we are to obtain any arbitrary velocity in all 6 dimensions, then it is necessary that the Jacobian matrix has 6 linearly independent columns. Thus, we can invert the Jacobian matrix and solve for Q dot. Okay. The rank of a matrix is the number of linearly independent columns or rows. So when the rank of the Jacobian matrix is equal to 6, we have a square matrix and we would be able to obtain the inverse of that. And as a result, the end effector of the manipulator can execute any arbitrary linear and angular velocity. Now for a matrix that belongs to R6 by n, the rank J would be less than or equal to the minimum of 6 and n. That is, for a two-link planar arm, we have n equal 2, therefore the rank of the Jacobian would be less than or equal to 2. For an anthropomorphic arm with spherical wrist, n should be equal to 6, and therefore the rank J would be less than or equal to 6. Very important thing to note is that the rank of a Jacobian matrix is not constant, and that should be evident if you look at the Jacobian matrix of a two-link planar manipulator. Even though we have terms like A1 and A2, the quantities such as sine theta 1, sine theta 1 plus theta 2, so those quantities will depend on the current configuration, right? Therefore, those are variables. And as a result, the Jacobian matrix is a variable and the rank, therefore, will change. Now we are ready to define the term singularity for a robotic manipulator. So the configurations for which the rank of the Jacobian matrix is less than its maximum value are called singularities or singular configurations. Okay. So at singularities, motion in certain directions would not be attainable. That is, at singularity, a certain bounded end effector velocity that we would like to achieve will correspond to maybe infinite joint velocity. Furthermore, at singularities, a certain bounded force and torque that we need to extract from the end effector will correspond to very large joint torques. Alright? And usually singularities occur at the boundaries of the manipulator workspace, but not always. And near the singularities, there may be infinitely many solutions or no solution at all to the inverse kinematics problem. Okay. Now let's find out how we can determine the singularities. Now one way to find the inverse of a square matrix is to obtain the adjoint matrix and scale it by the inverse of the determinant, right? So as you can see here in this expression, the inverse will not exist when the determinant is equal to 0, right? Now the Jacobian matrix naturally involves many nonlinear quantities, and therefore solving the determinant J equals 0 equation is difficult. Again, a spherical wrist can come to the rescue. That is, if the manipulator has a spherical wrist, we can solve this equation easily by decoupling the singularities. We already know that we can decouple inverse kinematics for a manipulator that has a spherical wrist. So in similar fashion, we can decouple singularities into two problems: the arm singularities and the wrist singularities. So the arm singularities result from arm motion, whereas the wrist singularities result from wrist motion. Now let's consider a manipulator having a 3 degree of freedom arm and a 3 degree of freedom spherical wrist. So our Jacobian matrix is going to be 6 by 6. Okay, and now we know that a given configuration would be singular if the determinant of the Jacobian matrix is equal to 0 at that configuration. So remember that only certain specific configurations out of all the possible configurations of the manipulator in the workspace would be singular. Understood? Let's partition the Jacobian matrix into 3 by 3 blocks, and the left half you would call that as JP, where P is for position, and the right half as JO, where O is orientation. So if we look at the original equation of C equals JQ dot, so if we expand J, we would have the first column of J times Q1 dot, second column of J times Q2 dot, third column of J times Q3 dot, fourth column times Q4 dot, and fifth column times Q5 dot, and finally the sixth column times Q6 dot. Okay, and in the Jacobian matrix, so we have these 6 columns, and we know that for this manipulator the first 3 joints determines the position, right? Position of the wrist center, and therefore these 3 columns would be denoted by JP, P for position, and the final 3 joints will determine the orientation of the wrist. Therefore we have these 3 columns denoted by J orientation, and this is a 6 by 6 matrix. Okay, for a spherical wrist we have the last 3 joints as revolute joints, so the ith column of the Jacobian would have this expression. Therefore I can write J0 as, so when I equals 4, we have Z0 3 cross T0 6 minus T0 3 and Z0 3, and when I equals 5, we have T0 4 Z0 4, and finally when I equals 6, we have Z0 5 cross T0 6 minus T0 5 and Z0 5. Okay. For a spherical wrist, we had O3, O4, O5 at a common point called the wrist center OC. Now if you look closely, frame 3 is actually the base frame of this spherical wrist arrangement, and it does not change when any of these 3 joints are actuated. So it should have been somewhere here, but for our convenience we moved it to the wrist center. Okay, this is joint 4, and when joint 4 is actuated, frame 4 will change, and this is joint 5, and when joint 5 is actuated, the frame 5 will change, and this is joint 6, and when joint 6 is actuated, frame 6 will change, right? So actually it would have been better we had frame 3 back here and had frames 4, 5 and 6 at the wrist center. And in that case we need one more frame, that is frame 7, which is at the end effector. Makes sense, right? Now all this discussion leads to some simplification where I'm going to place also O6 at the wrist center OC. Okay, now if we do that, I can write J0 as 0 Z0 3, and this will also become 0 Z0 4, and this will also become 0, and this is Z0 5. Now you must be confused about this new information and wondering whether we have a frame 7 at the end effector. Now let's say that this form of the Jacobian does not necessarily give the correct relation between the velocity of the end effector and the joint velocities, and this is intended only for learning purposes and to simplify the determination of singularities. Okay, with the simplified JO, the Jacobian matrix will have the block triangular form, that is J would be equal to J11, J21, and this part would be 0, and this is J22. So here we have the block triangular form, and this is actually JO. Okay, and the determinant of the manipulator Jacobian matrix, determinant J, would become the product of determinant J11 and determinant of J22. That's because of the block triangular form, right? And we already know that J11 has its ith column as z0 I minus 1 cross t0 n minus t0 I minus 1 if the joint is revolute, and it would have z0 I minus 1 if the joint is prismatic. Okay, and J22, that is actually this part, right? So that is equal to Z03, Z04 and Z05. Okay. As a result, the set of singular configurations would be the union of wrist configurations that satisfy determinant J22 equals 0 and the arm configurations that satisfy determinant J11 equals 0. So if we look at the wrist singularities first, then we have determinant J22, which is equal to the determinant of Z03, Z04 and Z05 equals 0, right? So this is satisfied when the vectors Z3, Z4 and Z5 are linearly dependent. Or in other words, when any two of these wrist joint axes are collinear, then we have a wrist singularity. Joint axes becoming collinear are the only singularities of the spherical wrist. And unless we impose some mechanical limits on the wrist design, they will be unavoidable. Okay? And in fact, when any two revolute joint axes of the manipulator are collinear, then there will be a singularity, because there will be no net motion of the end effector when an equal and opposite rotation happens on these axes. Now please note that collinear means they are on the same straight line, and that is different to being parallel. And for the arm singularities, we have to find the configurations where determinant J11 is equal to 0. And the I column of JVI is given by this expression. And here, ON will be replaced by the wrist center OC. Okay. Alright. Now let's look at some examples to reinforce what we learned. First, we will look at the 3-link articulated manipulator, and you can work out the Jacobian and you will find J11 to be this matrix, and please verify that as an exercise. Okay, and the determinant of J11 turns out to be this expression, and similarly you can verify this as an exercise. Now, to find the arm singularities, we need to find determinant J11 equals 0, right? So determinant J11 equals 0, and that happens when either S3 equals 0, that is sine theta 3. So from this we get theta 3 equals 0 or pi, and the next case is when the second term, that is A2 C2 plus A3 C23 equals 0. Okay, so when S3 is equal to 0, we get the following two configurations. So the first one is when theta 3 is equal to 0, and the second one is when theta 3 is equal to 180 degrees. This one is actually when the elbow is fully extended, and this is when the elbow is fully retracted, right? So with these configurations, you can understand that we cannot achieve any velocity v in this direction. Okay, and the second case is when A2 C2 plus A3 C23 is equal to 0, and that corresponds to this configuration on the right. Actually, we have come across this configuration when we were dealing with inverse kinematics as well. So here you can see the wrist center intersects with Z naught axis, right? Therefore, we cannot move the wrist center even if we actuate this first joint. Okay. And again, if we have an offset D, then the wrist center will not intersect with Z naught, and as a result, we can get rid of that particular arm singularity. Next, we will look at the spherical manipulator. As you can see in the diagram to the right, the manipulator will be in a singular configuration when the wrist center intersect with Z naught axis. And in fact, you can see the joint axis of the first joint and also the third joint has become collinear in this case, right? And as before, any rotation about joint 1 is unable to change the wrist center. Example 3, the scalar manipulator. So we have already derived the Jacobian matrix for the scalar manipulator, and the J11 part is this block, right, where alpha 1, alpha 2, alpha 3 and alpha 4 are given as follows. Now let's find determinant of J11, and that should be equal to 0 for the arm singularity, right? So we can write that as alpha 1 times minus alpha 4 and minus alpha 3 times minus alpha 2, and the remaining part is 0. So this would give us alpha 2 alpha 3 minus alpha 1 alpha 4, right? So from the quantities we have, we can write this as A1 C1 plus A2 C1 2, that is alpha 2, times alpha 3, so that is equal to A1 S1 2, and we have a minus sign. And next we have minus alpha 1, so that should be plus E1 S1 plus A2 S1 2 times alpha 4, which is equal to A1 C1 2. So this is equal to 0, right? So from this equation we see that A1 cancels off, and also this whole term of A2 C1 2, this term and that term would also cancel, right? And therefore we can write the remaining terms as minus A1 times C1 S1 2 and here we have minus S1 C1 2 equals 0, so A1 will also cancel. So this is actually sine theta 1 plus theta 2 minus theta 1, right? And theta 1 will also cancel. So finally we have sine theta 2 equals 0, and that gives us theta 2 equals 0 and pi. Okay. So the arm singularity will happen in the scalar manipulator when theta 2 equals 0. That means the link is fully extended, or else when theta 2 equals 180 degrees, that is when the link is fully retracted. Okay. Next, we are going to look at inverse velocity. We already know that the manipulator Jacobian matrix relates the Cartesian velocities of the end effector to the joint velocities of the manipulator, right? So finding the joint velocities for the desired end effector Cartesian velocities is the inverse velocity problem. When the Jacobian matrix J is square and when it is non-singular, Q dot can be easily found by inverting the Jacobian matrix. Okay. But for the manipulators that does not have exactly 6 links, we are unable to invert the J matrix. In that case, we can solve the inverse problem for Q dot if the rank of the augmented matrix J and the Cartesian velocities C, that is this part, is our augmented matrix. So when the rank of that augmented matrix is equal to the rank of the Jacobian matrix, then we can solve the above equation. Nevertheless, we will not going to deal with that problem in this course. Okay. For a robotic manipulator that has more than 6 links, now we call them as redundant manipulators. Okay. So for redundant manipulators, we can solve Q dot using something called the right pseudo inverse. So what is pseudo inverse? Now we can write J times J transpose, so that is some matrix, times its inverse should be equal to identity matrix, right? A matrix times its inverse, right? Now if I regroup this, I have J times J transpose J transpose inverse. Okay, so if I regroup this, that would be equal to identity, but then again a matrix times something is equal to identity matrix. So what can we say about this term? So it should be something similar to the inverse, right? So we are going to call that as J plus, and J plus is the right pseudo inverse. Now we can't call it the inverse because we don't know when we pre-multiply J with this guy whether we are getting an identity matrix or not, right? Therefore it's not the perfect inverse, but we know that when we post multiply J with this guy, we get identity matrix, right? Now from linear algebra, we have for a matrix m by n where m is less than n and rank is equal to m, the inverse of that matrix times the transpose would exist. Okay, so that result comes from linear algebra theory. Therefore, we can surely say that this part exists. Okay, therefore J plus or the right pseudo inverse exists. But in general, if we pre-multiply J with J plus, then it's not going to be equal to the identity matrix. Understood? Now let's take a manipulator having the degree of freedom equal to 8, right? So the Cartesian velocity vector is equal to the Jacobian matrix times the joint velocity vector. So here Q dot is going to be 8 by 1, right? Therefore J would be 6 by 8, right? And what about J times J transpose? So J is 6 by 8 and J transpose is 8 by 6, right? Therefore, we get a square matrix of 6 by 6. And from linear algebra, it says the inverse of this exists. Understood? Now for the case where n is greater than 6, the solution for q dot is given by the following expression, right? So here b is an arbitrary vector. Now let's check whether this is true or not. So we have q dot equals j plus c plus I minus j plus j. So here we have a pre-multiplication with j and b. Now let me pre-multiply this whole equation by the Jacobian matrix. So j times q dot is equal to j plus c plus j times I minus j plus j b. Okay. So what is j times j plus? So that is identity matrix, right? So we have j minus j times j plus j b, and again we have j times j plus, which is equal to identity matrix, right? So this is equal to c plus j minus j times b, which is the Cartesian velocities. Okay, so the solution given by the above expression is correct, and if we need to minimize joint velocities q dot, then we can choose b to be 0, because we are free to choose the b vector, right? With that, we have come to the end of this lecture. Let me summarize what we learned. So a singular configuration of a robotic manipulator is a configuration where the rank of the Jacobian matrix becomes less than its maximum value. The manipulator Jacobian matrix is not a constant matrix. It depends on the configuration. Therefore, the rank also changes with different configurations. We can determine manipulator singularities by using the determinant of the Jacobian matrix and make it equal to 0. For a 6 degree of freedom manipulator that has a spherical wrist, actually we are able to decouple arm singularities and wrist singularities. So the wrist singularities satisfy the equation determinant J22 equals 0, and the arm configurations satisfy the equation determinant of J11 equals 0. Thank you very much.